There's a lot to understand as we look at a standard three-tier architecture. Let's start by just looking at the network components as we look to build an application that begins with a front-end web server, that moves to an application server, and then communicates to a database running in a master standby configuration. We begin by looking at the physical infrastructure and the idea that even though we've got a three-tier application, we always think from the beginning about high availability. This means running in an AWS region with multiple availability zones. Now, every AWS region has at least 2 availability zones. You certainly can use more than 2, but for the simplicity of today's discussion, we're going to live in availability zone 1 and availability zone 2. You, of course, can spread across more if you need. Everything lives inside the VPC. For today, we've chosen the CIDR block of 10.10/16 as our networking component for the VPC, and then we've divided our assets into subnets. Everything that lives inside your VPC lives inside a subnet, and the subnets all have their own CIDR block. They cannot collide, they must be unique, and they all are a subset of the core VPC CIDR block itself. What we want to do is arrange communications in the subnets, always with the goal of protecting the assets. Because how do we want our architecture to be consumed? Do we ever want consumers out here in the internet communicating directly to the database? No, we never do. We always want them to go through the front application web servers, and from there, the application servers communicate with the app servers, the app server communicates with the database. But by protecting the database from any outside communication, we protect it against hacks, intrusions, or misuse. There are many lines of defense we're going to put around the sweet GUI center of your application. We start with the networking components. Instead of putting everything inside a single subnet, we divide our availability zones into public subnets and private subnets. If you've done on-premise networking, when you think about subnets, you start thinking about the switches and the routers and making sure that all the assets need to communicate with each other are on the same switch, the same router, and then other assets live on separate routers. In AWS, that's not the purpose of subnets. Now, there's a whole discussion about how AWS networks work under the hood. That's not the subject for today's conversation. If you want to know that, please watch a separate video called A Day in the Life of a Billion Packets. For today, we want to talk about the fact that any asset in the public subnet are assets that will have direct communication with the outside internet, and anything that is not supposed to be touched directly will live inside a private subnet. Could I have multiple private subnets? Of course you can. We are simplifying the diagram for instructional purposes. What makes something public? What makes something private? Again, it's access to the outside. Now, a VPC, by definition, is a virtual private cloud that allows no traffic in or out except authorized communication. Traffic in or out happens through the gateways. Now, the first gateway we talk about is the IGW, the Internet Gateway. And this is what allows communication from the outside internet to pass into your VPC and into whichever subnets are authorized. Well, that's our first step as we talk about routing. The VPC is designed to isolate traffic across any other VPC inside AWS. Well, any asset inside your VPC already knows how to send packets between itself and anyone else, any other component of the VPC. That's done through route tables. When you created the VPC, whether you created it in the console, whether you created it through an API, the default route table object was automatically created for you. Only has one line. In this case, it is the CIDR block of the VPC itself, 10.10/16. And where is the target? It's local. There's nothing else you have to do. But that means any asset inside the VPC, independent of its private IP address, independent of subnet, has a path to send the packet. It does not mean the packet's authorized. That's a later conversation we'll have about security groups and access control lists, but it means that the packet at least knows how to get to the other instance. But that's as far as it does. If you want a packet from an instance in the public subnet to be able to exit out the IGW and get out into the interwebs, or vice versa, if you want the interwebs to connect to your public instance, we have to add the route line that gives the path out through the IGW. We could put that access right into the default route table. The problem is that would apply to every instance, and the whole point of what we're doing is to protect that sweet GUI center right here. So instead we make a new object, the public route table. When you create a new route table, it automatically copies everything from the default route table, so it begins with 10.10.0.0/16. That stays local. Now what we want to do is we want to authorize the public route table, anyone associated with it, to have access to go out the IGW. Well, which IPs are we targeting? We're targeting the entire IPv4 spectrum. So how do we do that inside of notation? 0.0.0.0/ every address, 0 goes out the IGW. Now, the IGW is not a physical server, it's a network construct. It is a highly available network construct that says that any content that is targeted that does not fall under the 10.10/16 will automatically then allow to pass outside the region into wherever the DNS lookup sends it. Final thing we need to do is associate the public route table with the public subnets. Now, any packet originating from the web instance or targeted to the web instance, if it's going outside the 10.10/16, will now have a path to go out the IGW, find what it needs, and make the return. Because we have not added the 0.0.0/0 to our private subnets, if someone even knows the IP address of this instance, any attempt for a packet to pass into it will be summarily dropped. It will not touch this instance because there is no route line that allows the IGW to connect to this subnet. And you cannot hack what you cannot touch. Pretty cool. Except we have another problem, and that is at some point I might want this asset to be able to go out to the internet and pick up a patch. Let's say, for example, this is an Oracle database, and I need to go out to oracle.com and download the latest version of Oracle, update my system. Right now, here's exactly how that would happen. The instance would make a request to try to get out to the IGW. What it would do, DNS lookup, go to oracle.com, DNS would say, well, that's at 54.something something, I'm making the address up, at which point the instance would say, all right, send a packet off to 54.whatever. What's my route table? It's still associated with default route table. 54.whatever, is it part of 10.10/16? No, it's not. No other choice. Packet gets dropped. It cannot communicate out. So we need to add a few other elements to this architecture to make that happen. We could just associate the public route table. Problem with that is then we've exposed our assets, and I've violated all the security protocols I just spent time developing by making this subnet public. The name would still be called private, but because it has 000 IGW access, the subnet is, in fact, a public subnet. The name is irrelevant. You can call this man-bear-pig. I don't care what you call it. If it has 000 IGW access, it is a public subnet. How do we protect it? Well, we start by looking at the two paths of communication that we're trying to solve in this scenario. And the first path we're trying to solve is communication from the outside, because what you have is a DBA who wants to be able to get access to the database in the first place to see if it needs patching. I have a DBA out at Starbucks or wherever. She wants to log in and connect to the database. Right now, as it sits, there is no way for her packet to be accepted by the database. So we have to add another object into our architecture to make this happen. Again, we could assign the public route table. That violates every security mechanism we put in place so far. It's a new instance called a bastion host. And the whole idea of a bastion host, or a jump box, is to provide a landing place for your DBA or your system administrator to log into a public-facing instance. Once they're in there, they can then log into any other instance that they have the privileges to log into, because they're already inside the VPC. Now, the bastion host is going to have all sorts of security groups and access control list protections around it to prevent any unauthorized access into it. But assuming those are open, your DBA can now log into the bastion, and she will gain root access to that bastion host, at which point she can now connect from the bastion host directly to the database or wherever else she needs, because the public subnet has the local line, which means from there the packet to anywhere inside knows its path. Is it authorized or not? That's a different conversation. We'll assume it is. She now is at root on the database, and now she can log in and do whatever checks she needs, and discovers she needs to go to oracle.com, for example, and download the latest patch from wherever the repository is. Connecting over the bastion server still does not give her the access to initiate a packet from an instance and get back out the IGW. It doesn't just retrace its steps. So we need another object to then allow initiated traffic from a private subnet to again go out the IGW. Once again, we have to add something. So we use an old school trick. It's a NAT server, a network address translation server. This is not something new AWS has invented, and it works fairly simple. The NAT server simply pretends to be the entire internet. The database, on trying to log out, targets the NAT server thinking it's the whole internet. The NAT server basically says, yes, I accept, I am whatever address you're looking for, and then it redirects the packet. Well, to make that happen, we need a new route table. The private route table. We first make a copy, as always, of the default route table, which means we copy everything from the default table. So 10.10. 10.10.0.0/16, my local line, that's normal. The new line is, what do we do with the 000s? We don't go out the IGW. Instead, in this case, my 0.0.0.0/0 goes out the NAT ID. And we simply target all traffic destined to go outside to this particular instance. And then we associate the private route table with both private subnets. And now here's how the packet traffic goes. DBA is logged in at root from the database. She wants to now initiate a packet transfer out, so DNS lookup says you're going to 54. Who cares? Packet now wraps itself up, checks the route table, 54. Whatever, not part of 10.10. Do I have another option? Yep, 000s. We definitely match that. So you must be the entire internet. And the NAT says, yes, I am 54. Whatever. By the way, to make this work, you have to turn off source destination checking. That's on by default, and that's very important because that's what protects your asset from getting in a man-in-the-middle style attack. In this case, because it's off, the NAT can masquerade and say, yes, I am whatever you want me to be, I'm 54. Who cares? It's not, but it pretends to be. It then takes the packet, reloads it, it has access to the IGW because it has access to the public route table, it sends it out, collects the packet it needs, pulls it back in, repackages it, sends it back, and you've now completed the process. So, by having the private route table target the NAT, we can get out, or my public route tables can go out direct without needing the NAT access. In either case, when I need to initiate, it's there. Now, am I going to allow it or not? That's a permissions issue. That's another conversation. But at least now we have packets going out. There's one more piece of the puzzle I want to mention, and that's dealing with hybrid options. Because what if I don't even want my DBA to be able to connect from Starbucks? What if I want to require that she can only connect if she's logged into the private data center or over a VPN tunnel? So in that case, I have my private data center. So my private data center, in this case, I'm going to require that my DBA log in from the private data center. And now I'm going to build a VPN connection into the VPC. I'm not going to go over the IGW. Instead, I'm going to use a new gateway that's called the VGW, or the Virtual Private Gateway. I can now set up access by adding route table lines into whichever subnet I want direct communication from. So perhaps I want to allow my DBA to connect direct to the database if they're coming in from the private data center. So if my private data center uses an IP scheme of 172.68.0.0/16, I simply add that line. And where am I going? VGW access. So in this case, she would be able to communicate direct to the instance without needing to go over the Bastion server if and only if she initiated her communication directly from the private data center. Now, is that the best practice element? Every implementation is going to be unique, and you're going to make your own choices, but these become a default set of tools you'll want to consider as you start building out your networking options in an AWS virtual private cloud.